Hello, hello, hello again, everybody. Welcome back. Today we're doing section 2.5. This is an interesting section. It's all about compositions of functions. It's also a very important section because this is kind of what you really want to do when you finally make sense of what functions are and what they do. You want to start daisy chaining them together and nesting them and things like that. Let me pull up the slides and let's get started. Right, here we go. So we're going to do a very brief review of functions. I'm really hoping that by now you're feeling a lot more comfortable with functions, in particular, what is going in and what is coming out. I know I sound like a broken record. That's a good thing because this section in particular, you really, really need to understand what is going in and what is coming out. Because now what we're going to do is we're going to take functions and we're going to take the outputs and put them as inputs of another function. So, and we can do that as many times as we want. So we're going to do a quick review of functions. I won't dwell on it too long. Then we're going to talk about compositions. This is actually composing the functions. We're going to do a few examples. Then we're going to talk about decomposing functions, basically taking a function and breaking it into little pieces. And then we're going to talk about compositions on the mathematical horizon because you do use this a lot. All right. Let's get started. I'm going to breeze through this. Hopefully, this is all very familiar now. I know it gets reviewed on the homework and so on, the activities. A function is just a rule that assigns each element in the domain an element in the range. Remember that x in this case is the input, f of x is the output. Um, that's going to be really important here. Whatever is between these parentheses, that is what is going in. And then f of x, that symbol means the output. That symbol, you treat it as a whole piece. It's the output of the function. Um, Now, really often, we want to apply a function to some input and then take that result and then apply another function to that result. And in general, we want to run an initial input through several processes, just chewing it up, right? Chew, 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 to change it into something else. We also are going to want to take a complicated process, a complicated function, and decompose it into a sequence of simpler processes, right? You probably had to do this yourself. Just think about your life where you're like, oh man, how do I get cleaned up in the morning, right? Okay, let me break it down. Let me break it down into pieces. I need to brush my teeth. What does that mean? Okay, I need to put toothpaste on the toothbrush. That is decomposing a process, right? So we're going to talk about composing processes, functions, and decomposing processes, functions, right? So understanding how to do this is really, really important. You're going to need it a lot when you get into Calc 1. In particular, you're going to have to learn what's called the chain rule, which is a technique for differentiating compositions of functions. And in my opinion, it is actually the most important differentiation technique that you learn in Calc 1, and you'll use it forevermore after that. So it's a very critical skill, so make sure you are comfortable with it. Let's get a definition. There you go. So what is a composition of functions? Given two functions f and g with domains d sub f and d sub g respectively, and ranges r sub f and r sub g respectively, the composite function g of f is defined this way. So g of f of x means g of f of x, and we pronounce this symbol g of f of x. Okay? So very literally, we are taking the output f of x and we are putting it as an input of g. All right? So this is one where I want you to kind of stare at these slides for a second. Mull this over in your head. Okay, and now I want you to read it out loud to yourself and try to say it in your own words. Remember, you don't need to read it to anybody, it can just be to yourself. But say it out loud, it'll make a big difference. Right. Okay, now let's talk some more about this, and then we're going to do it a bunch of times, okay? So here's maybe some intuition for it. Remember before we had talked about functions as being these boxes that transform inputs into different outputs? That's what's going on here. So this was the original box, right? So, wait, hold on one second. Is this doing that thing again? Let me see. Is that, it's about the same, little bit of lag. Okay, so here x is going into the box f, and then what comes out is f of x, right? So that's the first function. What we're now going to do is we're going to take this output f of x and we're going to put it into another box. So we're going to take that output f of x, we're going to drop it into this box g, and what comes out? G of f of x. That is the composition process. Okay, that's the basic idea. So you can always come back to this to make sense of it. All right, you just got to really, really, really keep in mind what is going in and what is coming out. Hold on just one moment here. Let me fix something. Okay, sorry about that. All right. So let's get an important picture in mind. So the reason that compositions can be a little bit tricky to work with is this. Compositions of functions are defined sequentially. All right. There's an order to the composition. With g of f of x, the rule f is applied first and then the rule G is applied second. Okay, so we work from inside to out. So inputs and outputs, right? X goes into F. What comes out is F of X. And then we take F of X and we put it into G and we get out g of f of x. Okay, so inputs and outputs are critical here. You start with the input x, you plug that into f, then you get a result f of x, and you plug that into g. And if there's more functions that you're composing with, you keep going. All right. Now, because of that, this picture kind of shows you things here. So because we want to take outputs and treat them as inputs of another function, we have to really carefully consider the domains and ranges at play. So more specifically, this bold phrase right here, the range of the inner function must live at least partially in the domain of the outer function in order for the composition to make sense. Okay. Let me see, do I want to do, yeah. So take a look at this picture down here, this figure for a second. And let me show you what's drawn here. This is the domain of F. This is the range of F, and f goes from its domain to its range, just like that. Now, what we would like to do is we would like to take those results, those outputs of f, and we want to put them into G as an input. Well, here is the domain of G. It may not be the same as the range of f, right? Here is the domain of G, and here is the range of G, okay? So you'll notice here that there is an overlap. There's an overlapping region, and that region is critically important because this region completely determines what is actually going to pass through the composition. So, for example, here f takes x to this point, f of x, and luckily, whatever this value is, it's actually also in the domain of G. That means G can process it, G can operate on it. So G will take f of x and it will map it to G of f of x, all right? Now, pretend this happened instead. Let me put a point. I'm going to call this like x2 over here. Okay, now f is going to send x2 here to this point, f of x2. Now, notice the problem. F of x2 is not in the domain of G. It's not in the domain of G. So G cannot process this. You can't take x2, pass it through f to get f of x2, and then pass it through G. It won't work, right? That's because this point does not lie in this overlap. And what is this overlap? It's the intersection of these two sets. It's the intersection of these two sets. That's why we were talking about intersections earlier on in the chapter, because you really got to understand ranges, domains, and intersecting those sets. Let me clear this for just a second here. Right. Okay, so let me zoom in on this a bit. Really, really what I'm saying is this special region that you see pictured here, this one, this is the intersection of the range of f with the domain of G. That's the intersection. So every time we're looking, or every time we want to do a composition, it only makes sense for values that get passed into that intersection, right? That's the important part. Otherwise, you can't even do the composition. Makes no sense to do the composition if there's nothing that can go into it, right? Okay, keep that in mind. We're going to need that. That's why I say this again. It's really important to carefully consider the domains and the ranges of all the functions involved before you perform a composition. And finding them is not always straightforward. Okay, we're going to practice it now. We're going to practice it in the activity, and we're going to practice it on the homework. Uh, yeah, okay. Let's just try one, okay? Here I'm going to give two functions. Here's the function f of x equals the square root of x, and g of x equals the square root of 2 minus x. We're not going to do all of these. There's four, but we're going to do a couple. Let's find the domains of g of f of g, f of f, g of g, and then compute the compositions. We're going to find the domain first before we do the composition, because again, the composition doesn't make any sense if there's no domain of the composition. If you look at the definition of a function, it requires a domain to exist before you can define the rule itself. Like, it doesn't make sense to have a rule that doesn't apply to anything, right? So let's start with g of f. We're going to find the domain of g of f, and then we're going to do the composition g of f of x. Now, what I always recommend for these, first and foremost, every time you see a problem like this, find the domain and range of all the functions involved. That's what I've got right here. So here's f. Let's find the domain and range. We have some practice with this, right? So the domain of this function is 0 to infinity. The range also happens to be 0 to infinity, right? Remember the graph. This is one of those important graphs. Looks like that, okay? Now, that's for f. So we've got the domain and the range of f. Now let's do the same thing for g. What is the domain of g? Well, we need this thing to be non-negative. So the domain of g is whatever x values satisfy this. In other words, it's whatever values of x satisfy this inequality, or in other words, it's this interval from negative infinity to 2. All right. What is the range of G? Well, imagine the graph or sketch the graph or plot the graph using Desmos or something, and you'll find that the range is still 0 to infinity. Because again, this function here, G, this is just a transformation of the square root function. It's literally just reflecting and then shifting. That's pretty much all it is. Or maybe I should say shifting and then reflecting. That's a better way to put it. In fact, maybe I'll write it out here. This is actually, I'll write it as negative x plus 2. So then this is negative x minus 2. So you're shifting x to the right by 2 units and then reflecting it around that line, x equals 2. So you're getting a graph that looks like this, where this is a 2. That's the basic idea. So now we've got the domains, we've got the ranges. Now we consider what composition we would like to do. So we want to do g of f. So with g of f, f is happening first. So in order to do this, we need to look at well, we need to find the domain of the composition. So in order for this to even make sense, we need to consider the domain of the inner function f, but we also need the range of f and the domain of g to intersect, right? Remember, go back to this picture. We need to find this set. We're going to find this set, and then we're going to look backward to see what goes into that set. That's the idea. Okay, so this is how it's going to be for every composition you do. You need to look at the range of the inner function intersected with the domain of the outer function. In other words, for this one, it's range of f intersected with domain of g. Luckily, we calculated all those, so we can compute that intersection. Here we go. Yeah, so first of all, the domain of f is already 0 to infinity, so we have that restriction already. Now we're going to intersect the range of f and the domain of g, and we know how to do that computation now. Here we go. Range of f intersected with domain of g is the intersection of these two intervals, which is 0 to 2. All right. So what this means is that not every value of f of x is acceptable to the function g. There's a restriction. So it is very much like this. This overlap is not complete. There's only a little bit of an overlap. This is like, this and this, and they're not perfectly covering each other. There's some overlap and there's some not overlap. All right. But now that we know what that overlap is, we need to take this and we need to look back at the domain of f and see what goes in to this thing right here, what goes into that set. So because our function f is continuous, we're just going to look, and it's increasing, we're just going to look at the endpoints. We're going to look at the endpoints of that interval, and we're going to map backward. So we're going to look and see where f of x is equal to 0, and we're going to look and see where f of x is equal to 2, and then we're going to solve for x, all right? All right, 1 second. Okay, so yeah, like I was saying, we're going to set f of x equal to 0, and we're going to find the input that maps to 0. So that means this is equal to 0, which means this is equal to 0. And then we're going to do the same thing for when f of x equals 2. Square root of x equals 2 means x equals 4. And so, voila, the domain of our composition is the interval from 0 to 4, just like that. Okay, now that we know that this composition actually makes sense on some interval or just some space, now we can compute the composition itself. And that's a little more straightforward. We just plug the output of f of x as an input of g of x. So this is just a notational change here. F of x is the square root of x. Now everywhere in this formula where you see x, we're going to replace it with square root of x. So this becomes a square root of x. And then that's it. In this case, there's no other simplification we can do. We can just stop right there. That's it. Okay, so let's do another one. Let's do f of g next. We're not going to do all of them, but we'll just do a couple. Let's do this one next. So now the order has changed. G is now the inner function, and f is the outer function. So once again, in order for this composition to make sense, we need the range, the stuff coming out of G, to at least partially live in the domain of f, right? We need G to spit things out that are actually processable by f. So just like before, we're going to look at the range of the inner function intersected with the domain of the outer function, range of G intersecting domain of f, right? Now, in the very beginning, the domain of G already has this restriction. So we already know we can't put anything into this composition unless it is less than or equal to 2. So we already have that restriction. Now we're going to compute that intersection. Range of G intersect domain of F. Here's the calculation. These two intervals, when you intersect them, you get that. You get that again. So this is actually equal to the domain of f. This is equal to the domain of the outer function. So what that means is that any value of g of x is acceptable to the function f. So in this case, the intersection is whole. The Venn diagram is a circle, to use that meme, right? So this is a situation where this picture is not accurate. And what's happening is these two ovals are actually coinciding perfectly. There's a perfect overlap. All right. Let's see, where was I? Right here. There we go. Okay, so because any output of G is acceptable as an input of F, the domain of our composition is just the domain of the inner function, the domain of G. There we go. So G takes points from negative infinity to 2, and it spits them out in 0 to infinity. But f takes points in 0 to infinity and spits them out wherever it wants. So because this overlap is whole, the domain of the composition is just the domain of the inner function. Sweet. Now that we know that our rule, that our function can actually be defined somewhere, let's calculate the composition itself. Just like before, just remember, just keep in mind inputs and outputs. That's really all it is, inputs and outputs. It can seem more complicated than it is. Just follow your nose, what's going in, what's coming out. I'm taking this, I'm putting it in. You can do it, all right? So f of g of x is f of g of x. G of x, the output, is this formula right here. So we're going to plug it into f. So that means everywhere that you see an x in the function f, the formula for the function f, we're going to replace it with square root of 2 minus x. So that's what's going on right here. So the square root of square root of 2 minus x, just like that. Now, this one we can actually simplify a little bit. We're going to talk more about this kind of simplification in chapter 4, the very beginning of chapter 4, but we can write the square root of a number as a power of 1/2. So this is 2 minus x to the 1/2 to the power of 1/2. And remember properties of exponents. When you raise an exponent to an exponent, you get multiplication. So 1/2 times 1/2 is 1/4, which we can write as the fourth root of 2 minus x. Okay. And where is this defined? It's defined on the interval -infinity to 2. So we're all good. Everything's good. Okay. Now, this is one. Wait, what did I say there? Oh, typo there. I'll fix that later. I'll fix this one. This should say compute the compositions. Yeah, and remember these should be also a little bit switched. So if you're feeling up for it, try to find the domain of f of f, and then compute f of f, and then try to find the domain of g of g, and then compute g of g. And we're going to do similar problems in the activity, and you'll get some more practice on the homework. All right? Okay, let's do another example where we're using a different way of finding the domain. Remember when we talked about finding the domains of functions, you can either find all the numbers that work, or you can find the numbers that don't work and cut them out. So we're going to use that technique now. So here's the function f of x, 7 over x minus 3. G of x is 2 over 4 minus x. We're going to find the domains of these and then do at least one of these compositions. So let's start by finding the domain. Ooh, and actually, you know what? I want you to try this part. So let me throw up the thinker for a sec. Okay. Say something out loud to yourself. How would you find the domains of these rational functions? Okay. And now try to write the domains. See if you can also find the ranges. Remember how to find the range for now, graph it. So find the domain and the range of both of these functions, f and g. Okay. Now let's do it together. So the domain of f is everything except 3, because we can't divide by 3. The range of f is everything except 0. This never achieves the output 0. And you can see that if you pull up the graph on Desmos and look at it, you'll see it never achieves the value 0. For a more analytical approach, we'll actually explore these more in chapter 3, and you'll be able to graph these by hand when we get into chapter 3, but we're not there yet. Still got to get through chapter 2. Domain of G, everything except 4, and the range of G happens to be everything except 0. Okay, so let's do f of G first. We know right away that the domain of G already excludes 4. Wait, let me emphasize this. G is occurring first. So we're going to do G and then we're going to do F. Okay, G and then F. That's the idea. One second. Okay, there you go. G and then F. Yes, that's right, that's right. Okay, G and then F. So we're taking G, we're taking those outputs, and we're trying to plug them into F. But the issue is the domain of F excludes 3, right? So we don't want G to spit out 3, because if G spits out 3, and then we try to put that into the function F, we're going to have a problem. So what we really need to do is we need to find what value G sends to the number 3, and we need to cut that out. So that's what we're going to do right now. We want to find where G, the output of G, is equal to 3, and we want to omit that value from our domain. So G of x equals 3. Here's the formula for G of x. We're going to solve this for x. So multiply both sides by 4 minus x, you get this. Combine like terms, get the constants together, you get -10. Divide both sides by -3, and you get x equals 10/3. So what we just found out is that the function g sends the number 10/3 to the number 3. So this is the bad number. We don't want this in the domain of the composition, because g is going to send this number to 3, and then we're going to try to plug that number into f, and f doesn't like the number 3. All right? So we know what to cut out, and we already have the original restriction that x can't be 4, so the domain of our composition is this. It's all the real numbers as long as x is not 4 because of this problem, and x is not 10 thirds because 10 thirds gets mapped to 3, and f of x does not like 3. F does not like 3. There it is. Okay, now that we're aware of that, now that we know a composition is actually meaningful, let's compute the composition itself. And this is where you got to use some of that algebra that we talked about in chapter 1. It can get messy, but it's okay. Just take a deep breath. We have techniques for this. We're going to multiply by a clever 1 again, and we're going to get rid of all those compound fractions, or those complex fractions, right? So let's walk through it together step by step. I'll zoom in too. Hey, come here. There we go. So f of g of x means we're taking g of x and we're plugging it into f. There it is. So everywhere that f has an x, we're going to replace it with this whole expression, the whole thing. So just follow your nose, right? Follow your nose. Replace this with that, and you get this mess, right? Big mess. Ugh. If you feel a little anxiety when you see that, don't worry, that's normal. We're going to deal with it right now. We're going to multiply by a clever 1. This is a really, really handy technique, so watch carefully. I don't want to deal with fractions and fractions, at least not in this context, right? So what I'm going to do is I'm going to write 1 as 4 minus x over 4 minus x. And check this out. We're going to multiply the big fraction by 4 minus x over 4 minus x. And now we're just going to follow our nose. We're going to distribute 4 minus x to the top and get this. Now we're going to distribute 4 minus x to both terms in the denominator. This is going to go to here, and it's going to go to here. But when I multiply this term by 4 minus x, the denominators will cancel. Yay! And then we're just left with 2. And then when I multiply 4 minus x with 3, we just get 3 times 4 minus x. Boom. See, this is the step where you should feel like a breath of relief, where you're like, okay, no fractions. So it's that same technique. We're basically multiplying by, in fact, I'll write it like this. We're multiplying by LCD over LCD of all of the little fractions, the least common denominator of all the little fractions. We can talk more about that in class too. All right, now we just go through the usual process. So we're going to simplify. We're going to distribute 7. We're going to distribute 3 or negative 3. We're going to combine like terms, and then we get this. So this is the formula for the composition, f of g of x. That's the formula for the composition. Okay, now, little note about that. Yeah, here we go. So take a look at this formula that we just computed. Notice that it actually yields the fact that x cannot be 10 over 3. If you take this denominator here and you set it equal to 0 and you solve for x, you will get 10 thirds. So you could see just after the composition that 10 thirds does not work, so you would cut it out. But notice that the restriction that x is not equal to 4 does not show up here. This does not yield x equals 4 as a restriction, right? It doesn't. So this is why you can't simply compose the functions first and then find the domain of the composition. You may lose restrictions. So this is actually, let me see here. Yeah. Yeah. So this is where I will give a little bit of a spiel here. When it comes to finding the domain of a composition, there are all sorts of tricks and little techniques that you can learn. If you look it up on the internet, you'll find all sorts of little things where it's like, oh, if you see this function, do this. If you see that function, do that. If you see this other function, do this. If you see this type of a function, do that. Oh, if the domain happens to be this and the range is this, you can do that. Way too much to memorize, way too much to memorize. And the best part about this is in every single one of those cases, no matter what, you will still be considering this intersection, but they just won't tell you that that's the intersection you're considering. All right. No matter what, you have to consider this intersection in some way or another, period. How you do it, there's many, many different ways. But what I'm trying to do here is bring your attention to the fact that this is really the crux of everything. You got to find that intersection and then look back from that intersection to see what leads into it. The other thing I will say, the other cautionary note I will give, remember, functions don't have to be numerical in nature. Functions can be, there's nothing in the definition of a function that says it only applies to numbers. So if the techniques that you know for finding compositions of, I'm sorry, finding domains of compositions are all based on numerical function examples, what are you going to do when you don't have a numerical function? I'll tell you, you're going to do this. You're going to find the range of the inner function, intersect it with the domain of the outer function, and then you're going to look back and see what gets sent into that intersection. It'll always be that way, all right? Okay. Now, um, oh yeah, so if you're feeling up for it, try the other one on your own. See if you can do G of F. You can use the same techniques we did before. We've already got the range and domain calculated. So if you want to do that, I'll pause for a second so you can try it on your own if you'd like. Okay, now some important notes. Yeah, a couple important notes before we talk about decomposing functions. For one, in general, g of f is not equal to f of g. The order of the composition matters. You can't just switch the order and get the same result. Sorry. May not, or it may seem weird at first, but it's really not if you remember that a function is basically a rule. It's a process that you want to do, right? Switching the order of processes doesn't always give you the same result. Um, I always use this example. Imagine when you put on your socks and then your shoes, right? You get a very different result if you put your shoes on and then your socks. That's not the same thing. One of them you'll want to walk outside with, the other one you probably won't. All right. So keep that in mind. The order does matter. Switching the order does not necessarily give you the same result. The other thing I want to emphasize that I've mentioned before is that compositions don't need to be just two layers. They can be any number of layers. You can have any finite number of layers, a million layers, a trillion layers. And a lot of interesting results occur when you take the limit to infinitely many layers. Like what happens if you kept composing this rule over and over forever? What happens, right? That's where things get super interesting. Okay. Now we got to talk about decomposing functions. So this is a little bit easier. You just have to know what to look for. So we're going to take this function, and I want you to try this one on your own. Take this function h of x, and I want you to express it in the form of a composition by decomposing it into two component functions, f and g. And just remember, there's a nesting going on. There's an inner function and an outer function. Okay. So think about this for a moment, right? Say something out loud about what you would try. Maybe try to identify F and G, right? And then try to work it out on your own. We'll do it together in a moment. Okay. All right. Now, realistically, what we are looking for is inner function and outer function. And here we're only cutting it, only decomposing it into two pieces. So what is like the inside function and what is the outside function? Here they are. Let f of x equal x squared plus 1, and let g of x equal x to the 50th. Then, when you compose these two functions in that order, f and then g, you'll see that you actually get h of x. So h of x is equal to, actually, I should have put h of x over here instead, like that. G of f of x is g of x squared plus 1. But then G raises all of its inputs to the 50th power. So it's going to raise this input to the 50th power. And lo and behold, that is h of x. So we've written h of x as a composition of functions. We decomposed it. Okay. All right, let's do another example. This one, it's actually going to have three layers. So I want you to try this on your own. See if you can express this function in the form c of b of a by decomposing it into three component functions, a, b, and c. Okay, so you can think about it for a minute. Say something out loud about what you will try, and then try to work it out on your own. Remember, work from inside to out. What happens to X first? And then what happens to that result? And then what happens to that result? Try that. Okay, here we go. Now, when I look at this, what I see first is X is getting squared, and then I get X squared. Then what happens is I take that value and I subtract it from 25. That's what happens next. Then I take that value and I square root it. That's what happens third. That is the sequence of the composition. X squared, 25 minus that, square root of that. So our three component functions have this form. Let a of x be x squared. Let b of x be 25 minus x. Let c of x be the square root of x. Okay, and then when you do that, see, yeah, I should put these on the other side. I will after this. C of b of a of x is c of b of x squared, which is c of 25 minus x squared, right? Because we're taking x squared and plugging it in to b, which gives us that. Then we're taking this and we're plugging it into c, and we get square root of 25 minus x squared, which is h of x. Cool stuff. Okay. All right. Now, a lot of stuff there, but just to leave you thinking a little bit more, I want to kind of bend your brain for a moment. Compositions and repeated compositions show up a lot in more advanced mathematics. Frankly, if you're into machine learning and AI and that kind of stuff, it happens a lot because you can talk about a neural network and how many layers it has. And it is quite literally taking a function, taking an input, applying a function to it, getting an output, and then applying that output to another function, and then doing that any number of times. And you could have any number of layers in your neural network. So this stuff has applications well beyond calculus. You can use it for lots and lots of things. Oh, same thing if any of you are CS majors, right? CS majors, if you do a lot of object-oriented programming, or even if you're just building your own functions in whatever programming language you're using, you're going to do a lot of composing of functions. You're going to get a function that you design that takes an input and it spits out an output, and you're going to take that output, you're going to put it into another function, get a result, and boom, 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 boom. So these concepts are critically important. So here's something I want you to ponder just to get your brain thinking. What happens if you apply the same function over and over to some input? So instead of doing like f of g of h of x or whatever, what if you did f of f of f of f of f of f of x any number of times, right? Let's try this function. What about the squaring function, the function that squares its input? My question to you is, what if you repeatedly compose this function with itself? What happens? Ponder it for a sec. F of f of f of x. X squared, 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 squared. Ponder it, right? So while you're pondering that, my question to you is, what happens, first of all? And are there any fixed points? Meaning, are there any values that stay fixed no matter how many times you square them? Can you think of a number where if you square it and 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 square it, you just keep getting the same number over and over and over again? Think about it. Cool stuff. Here's if you want to go down a deeper rabbit hole. What I'm really talking about when I'm talking about these repeated applications of the same function, it can be generalized to what are called dynamical systems. Many of you are going to study dynamical systems. It also relates to what are called continued fractions. These are basically fractions in fractions in fractions in fractions. Sounds like I'm saying infraction. Um, Fractions that have bunch of little fractions in them, possibly infinitely many. And this actually ties into what's called the Gauss-Kuzmin-Wersing operator. This is the function or the operator that produces continued fractions. So all sorts of cool stuff. Another cool thing, when you get to linear algebra and you learn about matrix multiplication, maybe some of you already saw it before. Matrix multiplication is defined so that it's equivalent to a composition of linear functions. So quite literally, matrix multiplication is function composition of linear functions. That's what it is, all right? So cool stuff to think about. On that note, let's play. Let's do the activity for this. I'm excited to work with you as always. Your instructors are excited to work with you, your tutors. Ask questions, ponder these things, think big, let your mind wander, and I'll see you next time. Thank you again for watching.